look at this type of authentication, behavioral authentication, like do you think of it as a second factor authentication, considering those different parameters, how it changes, and also considering the high error rate?
So we've actually commercialized a solution. The feature is not exactly the same into Samsung Knox Workspace. So we actually try to protect, so these are B2B customers who pay a lot of money. So if someone can guess your password on the Knox Skill Workspace, we use keystroke dynamics to actually lock users out if unknown behavior is detected. So it's used to enhance security, not usability in that case.
Okay.
Yeah.
Thank you. We are moving to the next paper, fingerprinting IoT devices using latent physical side channels. It will be presented by Justin from UCLA.
All right, thank you for the introduction. And as you said, my name is Justin, and I'll be discussing our paper, Fingerprinting IoT Devices Using Latent Physical Side Channels. And before I begin this presentation, I'd like to thank my fellow collaborators on this work and all the hard work they contributed to this paper. So how are devices typically authenticated? One method is via cryptographic means, where we have a device here and it participates in some secure protocol with our receiver, which then is able to understand which device this is. Another method is via fingerprinting, where we analyze this transmitted signal that we are seeing, and then we're able to identify which device this is. And this is typically dependent on the transmitter module itself, as well as the protocol being used to communicate. The question I'm going to be posing today is there a way that we can authenticate these devices that is independent of, say, a secure protocol or the transmitter module and or protocol? And that's where I'm going to be looking at this electromagnetic side channel, where we can say, look at this latent signal that is being emanated from our device that is, say, independent of a secure protocol and or a transmitter module, and then we're able to understand which device this is. So the goal is to provide a more generalized form of authentication via this approach. So really quickly, what a side channel is, for those that aren't familiar, is it's typically used by an adversary to uncover some sensitive information about a device by observing some form of signals or behavior, such as, say, a power analysis, or let's say timing or temperature. We can uncover some sensitive information that is being unintentionally leaked. So in our previous work, we were able to utilize this electromagnetic side channel to communicate with the outside world. What I'm going to pose today is how else can we leverage side channels to do something useful, in which case, in this paper, we are going to be discussing how we can utilize side channels to fingerprint our devices. So here we have, say, an embedded device that is running a certain set of instructions, and the way that this side channel is going to be working is that we have, each processor has, say, like a clock that's going to be, say, running this processor, and the way that this side channel is produced is that there's basically a set of like switching behaviors from the transistors and capacitors in the processor, which then emanates this electromagnetic signal into space, which can then be observed at range. And this creates a unique frequency response that can then be analyzed. So specifically what we have here is we have, say, one device, and basically the way that we have our processor is that we have a voltage versus time characteristic that has, say, like a certain amplitude and period based on the specific device and the clock that is in this device, and we have a specific frequency response. Now, if we have another device, this device is going to have its own clock and its own processor, and what we'll see is we'll have a different set of, say, amplitudes and periods for this voltage and time response, which will then produce a different frequency response. So what we're seeing here is that each device's clock and its relationship to its processor is going to create this unique emanation in frequency, which we're then going to be leveraging to then fingerprint these devices. So here's our fingerprinting pipeline, and first we have our signals that we're going to be collecting from our devices, and so we need to be able to collect them. So here we have a picture of the spectrum, and note that our clock experiences harmonic behavior, so we can basically look at increments of the clock's base frequency in the spectrum and basically collect a broader view of our signal in order to fingerprint our device. And note that we are collecting both the clock as well as just ambient signals from the room. So we need to do, say, further work to filter out these unwanted signals and to focus on the signals that are relevant to our IoT devices. So this is where we have our pre-processing step, which you can further look at in our paper. But for instance, we need to slice up our data in time and do some form of, say, transformations and averaging in order to basically boost our signal and reduce the noise. Once we pre-process our data, we need to extract useful features that can help us identify this device. So here, I basically lay out a set of features that we utilize in our paper. If you want to learn more about these features, definitely refer to our paper, but the short story is that we want to collect a wide range of features in various domains in order to give our authenticator the biggest view of our device and basically different viewpoints in order to give us the best performance. Finally, once we have extracted our features, we then put these features into an ML classifier to then output our decision, which can consist of two things. It can consist of the ID, which is which board we are looking at, and then also the mode, which is also like what state this device is in. Really quickly, we can also, instead of the feature extraction and ML classifier steps 3 and 4, we can also replace that with a deep neural network in order to automatically detect these features and run classification. For the sake of time, I'm not going to be discussing this approach, but if you're interested, definitely refer to our paper and we do some tests and comparison. So to test this authentication performance, we need to test a wide range of experiments, and what we see here is we have, say, like a long-term study, temperature test, and things like this in order to give our, in order to test our system in a wide variety of IoT scenarios that we might see to see whether this approach could be realizable in reality. And so what we have here is we have our experimental setup where we have in our lab, we have our device as well as our receiver. We use just a commercial off-the-shelf TV antenna, and on the right-hand side, we have various devices. So for instance, we use an Arduino Uno as well as STM32s in order to test our experiments. So here are some of our results for this, for our fingerprinting approach. And note that all these tests are tested independently, so these percentages aren't cumulative. But if you want to think about the performance of our overall system, you can kind of think of this accuracy as, say, an average of all these tests. So just note that the accuracy is above 90% in most cases, showing that this work could be generalizable to a wide variety of IoT scenarios. So we believe that this approach could be very exciting in a few wide variety of applications, and the first one is hidden devices. So in a big problem that we're facing today is they have devices that say might be in our room, and we want to be able to identify them. So for instance, what we show after our results section is that we can basically identify a device that is say outside of the set. And we can basically say that with our fingerprinting module that there is basically a hidden device detected. Another application that is exciting is device state. So why not say only identify the identity, but why don't we identify what state is in? So basically in order to identify even more, understand what our device is doing even in a greater granularity. So we're looking at say an active state versus an idle state. And so here, in our results section, we also show that we're able to identify that a device is in the active state. And note that for these applications, we also test multiple devices active at the same time in our experiments. And to the best of our knowledge, that this approach has not been conducted much in many previous works. So in short, we propose Digitus, which is a means of authenticating our embedded devices via their latent signals. And in future work, we hope to further refine our MO model selection and as well as refinement of our model. Also look into the specific protocols to make our system more realizable and also generalizable to more kinds of devices. So thank you.
Thank you very much. Time for a very quick question. If there is any question.
Hi, thank you. A very interesting work, and I'm wondering how many devices can be detected at the same time?
Yeah, that's a good question. So we have a intra-device study where we conducted, we had 10 Arduino Unos in one study, and we were able to classify with greater than 90% accuracy. So definitely we believe that this work can be scalable, but definitely more work can be done to, say, test the scalability across even more devices and more types of devices. Yeah, so each device has a unique characteristic. So basically with our feature selection, we're able to distinguish between these different devices sufficiently. So you need to have a good understanding of the devices, and this is partly the feature extraction step. But also even in the deep learning side as well, you can do things to basically focus in on specific devices. So there are things that can be done, yeah.
The presenter for the 5th paper also has another paper to present in parallel in the other session. So we might have to switch and accommodate that out of sequence. Sorry about that. So I'm switching to the ISWC note now. ISWC notes will have only 4 minutes. These are very short presentations. So can I ask the author of the next ISWC note, which is C, Authentication, exploring the feasibility using egocentric view of face contour